When we talk about rational functions, this is the parent graph, y equals 1 over x. Remember, a rational function basically refers to something where you have the variable in the denominator. So let's see what this parent graph looks like. And the best way to get started is let's just plug in some points for x, see what we get for y, and then see how the graph looks. What this function is saying is that y is just the reciprocal of x. It's 1 over x. So we can just put in the reciprocals of all these numbers. I'm going to leave that one for a second. So 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third. Going back to this one, 1 over 0 is undefined. So we'll see what that does in a moment. But there are some points we can put in. So let me put in some of these points. We've got -3 and 1/3. We've got -2, -1/2, -1 there. And then we'll have a similar thing on the other side. So we've got 1, 1. We've got 2, 1/2, and 3, 1/3. And in fact, let's put in a couple more. Let's put in some fractions for x. So let's put in -1/2 and +1/2 for x. And the reciprocals of those would give us -2 and +2 for y. So I'll put those points in as well. When x is -1/2, y is -2. And when x is +1/2, y is +2. And maybe that will give us a bit more of an idea of the shape. So this graph is going to be in two separate parts here. That, and then similar looking thing on the other side here. Okay. What happens at x equals 0? Well, that's undefined. And that means that there's a vertical asymptote there. Pretty much every rational function that you're going to graph is going to have a vertical asymptote somewhere, because if there's a variable in the denominator, then there will be some spot where the denominator equals 0, and that's undefined. So remember, asymptotes get dashed lines. So I'm going to put in a dashed line asymptote at x equals 0. You might notice there's also a horizontal asymptote at y equals 0. So let me put that in and we'll explain why that's the case. So I kind of missed a little bit, but that should be right on the x-axis at y equals 0. So this is a vertical asymptote, horizontal asymptote at y equals 0. Why is that? Well, can this expression ever equal 0? Can 1 over x ever equal 0? Well, no. The only way for something to equal 0 is to be 0 over something. 0 over basically anything would equal 0. 1 over something can never equal 0. Now, when x is very large, let's say x is 1,000,000, y equals 1 over 1,000,000. It gets very, very close to 0. But this can never become 0. And the idea that you can get very, very close to something but never actually reach it, that's exactly what an asymptote represents. So this is not possible. Therefore, there's a horizontal asymptote. So in total, the parent graph, y equals 1 over x, has these two separate pieces. It has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. By the way, one more way of thinking of this relationship. So if we take this definition here, y equals 1 over x, and just to change the format, we multiply both sides by x. What we'd get is xy equals 1. And this might be another format, or maybe an easier format to see that, yeah, when x gets bigger, y gets smaller, because they always have to multiply out to the same thing. And when x gets smaller, y gets bigger. So this is the parent graph. And like all of the other kinds of graphing that we've done, now we can do transformations and slightly different versions of this. So let's start with one that's not going to be too different. Y equals 1 over x minus 2. And from all the graphs that we've done, we know what that tends to represent. Notice that when we set this up, what we're finding is, where is the denominator going to equal 0? Therefore, where will it be undefined? And therefore, where is the vertical asymptote? So this means that there's going to be a vertical asymptote. Remember on the last one, it was at x equals 0. This just means it shifted 2 to the right. So I'll draw in a vertical asymptote at x equals 2. So vertical asymptote at x equals 2. There's no vertical shift. We'll see one of those in a moment, but there's no vertical shift on this one. So the horizontal asymptote is right where it normally is at y equals 0. So we know the general shape this is going to take. It's going to do that sort of thing. You can always, and it's probably a good idea, you can always find like a point or two if that is a more comfortable thing, just to make sure you know where the graph is going. So I could plug in, sort of anything into there, but I'll just plug in x equals 3, y equals 1 over x minus 2, so 3 minus 2 equals 1. So that gives me a point to go off of when x is 3, y is 1. So I'll put that in there. And now I have, just sort of a point to make sure I'm going through the right place. We could sort of know that this point is reflected on the other side, but you could also, let's say, plug in x equals 1, y equals 1 over 1 minus 2, so negative 1. So when x is 1, y is negative 1. And that is indeed that point. So start by the asymptote, curve down. And the reason it would help to have a point is we know the general shape, but we might not be sure if it's like out there or back up here. So it will make your graph a little bit more accurate. I'll be clear on tests or quizzes if I am expecting you to find points or if it's sort of optional and we just want the general shape. But it's usually a good idea. All right, let's do one more of these. So now we have sort of all the transformations that we've become used to seeing. There's a negative sign in front, there's a horizontal shift, there's a vertical shift, there's an amplitude change. So again, all the same transformations that we've seen in so many of the other functions that we've done. We'll start with horizontal shift. So that means vertical asymptote at x equals negative 1. And I'll label that. We also now have a vertical shift, which we didn't see in the last couple, but we've got one of those now. So we can just see it's up 3. So instead of a horizontal asymptote at y equals 0, now it's up 3, it's at y equals 3. Oops. Okay, so there's a vertical asymptote, horizontal asymptote at y equals 3. This negative sign means that things are going to flip. So we're used to seeing these directions. Now we know it's going to be flipped across this line in both cases. But we can also, let's get a couple of points here just to make sure. So I will plug in, let's see, x equals 1 looks like it'll be easy math. So let's do that. So when x equals 1, y equals negative 2 over 1 plus 1 is 2 plus 3. So that's negative 1 plus 3 is 2. So we have this point when x is 1, y is 2. So let's put that on there. When x is 1, y is 2. And so now we have something to sort of aim our line at. And then let's do something on this side, just to make sure. So we'll do x equals -2. So when x equals -2, we get y equals -2 over -2 plus 1 is -1 plus 3. So that'll be 2 plus 3 is 5. So we have this point -2, 5. So -1, -2, that's 3, 4, 5. And you can see it's still a mirror on the other side, but this point would have been a little bit tricky to mirror. Like, does it go that way? Does it go that? So again, if there's even the slightest bit of doubt, we'll just find a point. And that would be our completed graph. So in summary, graphs of this sort of rational function where the parent graph is y equals 1 over x. There's always a horizontal asymptote. There's always a vertical asymptote. They're subject to the usual horizontal and vertical shifts that we've seen before. And the graph is always going to be in two parts, sort of in opposite quadrants. If it's positive, you'll have low left and high right. If there's a negative sign in front, you'll have high left and low right.